Okay, so let's start. Uh, so the prior is very important information, and it's usually free because it will be given by your program, or in some applications it's just available. And if you don't use it, you're wasting your information. Okay, so now since we have prior, which is this pH0 and pH1, so the Bayesian philosophy in our probability theory tells us that uh, the probability of error is that when H1 is true, you are making a decision for H0. Right? This is one type of error. The other type of error is when you have H1 true and you are making a decision for when H0 is true, you're making a decision for H1. That is another type of error. So think about it, right? The binary problems. If it's multiple hypotheses, then the error event will be more complicated. But for binary, we have only two type of error. And as you may know, previously we said this is a type 1 error, type 2 error, or we have different names, for example, probability of false alarm, probability of mix, something like that. This is false alarm, and this is probability of miss. But whatever, it doesn't matter, right? It doesn't matter. The point is we want to make error as small as possible. So we can define a probability of error PE like this, and it's equal to something like that. And to go from here to here, I want you to recall the Bayesian philosophy, or sometimes people call it Bayesian principle. In what? In in the probability theory. In the probability theory, conditional H1, you are making an error. Conditional H0, you are making an error, and it has to multiply with its prior probability. Prior probability. And then the minimal error detector, uh, it is like this. You have a probability of x conditional h1. In fact, you just multiply it back. You find out uh, it is in fact probability of x conditional h1 multiplied by h1. And if you get this term back to here, it's x conditional h0, p of ph0. Okay, so similar to the NP test, we'll compare the conditional likelihood ratio to a threshold. Conditional likelihood ratio to a threshold. Except that the threshold is set by its ratio of prior probability P of H0 and P of H1, which is equal to gamma. But this gamma is just a notation. The point is P of H0 and P of H1. That is the thing we're looking for. Okay. Equivalently, uh, here, right? This is what I just said. The threshold is determined by the prior probability, which means this term. If, in the common case, the prior probability are equal, then we will decide H1 if something like this, because when they are equal, this is equal to 1, so it will be this larger than that. Then, equivalently, we say that we will choose the hypothesis with the larger conditional likelihood, or the one that maximizes PXHI. This is called the maximum likelihood detector because this is likelihood. As I said, it looks like a probability, but in fact it's likelihood. Just because when you are making decisions, the samples, observations are already available. And when they are available, then this is calculated like a probability density function, but it's a function of hypothesis. It's not a function of variable anymore. So we call it a likelihood, and this is called a maximum likelihood detector. Okay, so let's take a look at one example. Uh, so we're at page 78, probably page 78. Okay. Just for you to, for some people, if you get lost, then you can follow up with the page number. The DC label in white Gaussian noise, the minimum PE criteria. This is a classical problem. We have a detection problem H0, H1, which is equal to this, which is equal to this, right? We have seen this before, except that we have multiple samples other than just one sample, where A larger than 0, and Wn is the white Gaussian noise is variance sigma square. If this is a digital communication problem where we transmit either S0 equal to 0 or S1 equal to A, right? Then it will goes like this, right? Digital communication problem. So this is just to illustrate that mathematical problems usually starts with mathematics with a model, while in fact it comes from engineering scenarios. So we are assuming this could be a digital communication problem. It could be other types of engineering problem, other than just digital communication, right? But digital communication is very common, so we say that it could be a digital communication problem. It could be other types of problem. Okay, if you say image processing problem, you say uh, uh, power system problem. You are detecting whether or not the power system has an error. It could be modeled like this. You're talking about control problem. It could be modeled like this. So there are many different types of problem can be modeled like this. But we say if this is a digital communication problem and we send signal 0 or A like this, then it's called, of course, the terminology is called on-off key or OK communication system. Then it would be reasonable that we assume prior equal to 1/2, right? The prior is set as 1/2。在数位通讯系统里面，我们对于所谓的0跟1这件事情，并没有偏好，而且事实上它并没有不均等的现象的哈。主要是因为数位通讯系统的前端、后端都会有说 error correction code 啊，还有一些 codec 的压缩等等的这些东西，它会把它会把呃它会把这个0跟1压到最后0跟1的几率会非常的随机，然后就会变成1/2。但是有些问题不一定这样子，譬如说像我刚才举的沙漠有没有下雨这个例子，这个例子很明显它不会均等哦，但是数位通讯系统通常usually in digital communications each hypothesis has equal probabilities, so it's 1/2. Okay, then the receiver that minimize PE is given by gamma equal to 1. This is 3.13 by using this equation. So we will decide H1. We are at page 79. We'll decide H1 if this is larger than 1. And this is what? This is in fact the probability of X condition on H1, right? This is condition on H1. 这是一个 multiple sample 的 Gaussian distribution condition on H1，因为 condition on H1，所以它就会有 A 作为它的 mean 哦。我想我稍微讲慢一点点，因为这 multiple sample 可能大家如果一时不熟悉的话，可能比较难跟上。This we have a multiple samples. Remember this? We have multiple samples instead of just one sample. We have multiple samples. So I want you to think about. I'm not going back to that page again, but I want you to think about. In previous class, we talked about probability density function for multiple samples, which is the vector version of Gaussian random variable. 回忆一下我们先前讲到那个矩阵版本的 Gaussian distribution 那件事情。Okay, so if you recall that vector version of Gaussian distribution, you 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 have multiple samples. In fact, it is a vector of Gaussian random variables. And then when you write its probability density function out, you simplified it, you get this with mean equal to A. But if it's conditional H0, then you get this. This is supposed to be minus something, but that something is 0. As a result, you have x squared. Okay, so you get something like this with mean A with mean 0. Then from here to here, it's just mathematics. You cancel this out, exponent, things can be simplified, you take log, something like that, then you get this, which is a lot simpler, right? Then you get what? Your decision criteria. 最重要的就是我们要导出 decision criteria. 那decision criteria 根据这个式子哦，你就是注意看哦，题目给你什么 ？They have given you sigma square. They given you A. They have given you N. They given you A. So everything is given except X, right? But X is not supposed to be given because it's from observation. So as a result, you simplified it, you find that we will make a decision for X bar. X bar is summation of X divided by N. Okay, it's the mean of the sample mean, So it's X bar larger than A over 2. This is the same form of the detector as for the NP criteria, except for the threshold. To determine PE, we use 3.12 and note that X bar actually is the Gaussian distribution of 0, and then its mean is sigma squared over N. This can be from your undergraduate probability 大学部的几率课程，你再回忆一下，如果一个 sample mean 除以它的 summation of sample 除以 n 的话，它的variance 是什么？就是这个。好，我就不再重复证明了，但是我想你们可以回忆一下。Then x bar condition on H1, it will be A with this. And therefore, our PE will be 1/2 something like this. Conditional H1, you make a decision for H0. Conditional H0, you make a decision for H1, and things like that. You go on, and then for condition on this is smaller than a over 2, right? 这一件事情跟这一件事情是逻辑上是等效的，这个可以理解吗？好，希望你可以理解，因为我们的 decision criteria 是大于a 就做 h1，所以要说 h0 就是小于a。OK，所以这件事跟这件事是刚好反面这样子。这一件事跟这一件事就是同面，为什么？We are making the decision x bar larger than a over 2, and then this is x bar larger than a over 2, right? So a lot of things they are just in different notations, well in fact they means the same thing. Okay, but just mathematically, they are given different ways of writing, different ways of notation, but they mean the same thing. And then for this thing, it will be 1 minus q function. And of course, I want you to just recall the q function. And for this thing, it will be just q function. And q function has some properties. So we have finally reached this point. Just use this equation and put it into here and simplify it, and you get something like that. As a result, the probability of error will be given here. Then it decreases monotonically with this, which of course the detection coefficient, Uh, I want you to just notice this term mathematically, and also I want you to understand a little bit about its engineering implications. 它工程上的含义是什么？ You have A over sigma square. So if you have sigma square smaller, you get better performance. If you have A larger, you get better performance. So let's come back and see if it's reasonable in our problem. It's in fact reasonable. You have a noise, you have a signal, and now if the signal is large compared to 0 is large, it's good, right? You get better performance. That's reasonable. And the other thing is sigma square. If sigma square is smaller, what it means is you have noise variance to be smaller. This variance to be smaller. And of course, you get better performance. So the mathematical outcome is consistent with our intuition in the problem. That's very important, right? So 数学的结果跟我们对于这个工程问题的那种理解跟直觉是一致的。这个一致性很重要，因为如果不一致的话，那我们是要怀疑什么？我们可能要怀疑我们是不是算错了哦。当然也有很多问题，算出来就是跟我们的直觉不一样。那这时候更重要了，因为我们不能根据我们的直觉去做设计，对不对？好，这就是在工程设计上，很多时候我们的直觉跟结果一样，很多时候我们的直觉跟结果不一样，不一样的话就要加强再检视一下，到底是不是有算错还是怎么样的哈。OK， then another form of PE follows from 3.13. Then we decide H1 if it's this. But from base rule, we have something like that, right? This is the base, just a pure base rule. It doesn't make any important changes. It's just a pure base rule. You get P of this equal to this. Then the denominator does not depend on the true hypothesis, and it becomes a normalization factor that can be written as something like that. As a result, we decide H1 if this is larger than that, right? 就是把这一项都用这个方式换掉，这一项都用这个方式换掉，然后 px 对两者来讲是一样的，因此 cancel out，cancel out 之后再简化，你就得到这个东西。So is this reasonable? The answer is yes. It's absolutely just a consistent and very concise form，它就是一个非常工整的一个 likelihood 的一个 form，就是 P 的 H1 likelihood 大于 H0，我们就 decide H1。So this is a very concise form of likelihood comparison， likelihood 互相比较的一个 form 这样而已。OK， so we will choose the posteriori probability maximum. Okay, so this detector, which minimizes P for any prior probability, is termed maxima a posteriori probability detector. Okay, so just think about it, and I'm going to stop and take a break for a couple minutes, then we'll come back.